Hi everyone, we are 3 students of COMP 90054, AI Planning for Autonomy. Our team name is ArtificialIdiot. Next, we will explain and demonstrate our designing for the second project, Pac-Man Capture the Flag contest, based on these parts. Hope you enjoy this video. Part 1, Main Challenges. In this project, we can control 2 role-acting Pac-Man or Ghost and coordinately eat foods on the opponent's side, while defend our own home side. When designing both defensive and offensive strategies, how to deal with the following challenges is vital to the victory of games. First of all, Pac-Man only has a limited perspective. Agents can only observe an opponent's configuration if they are within 5 squares distance, which means it is difficult for our defensive staff to detect streaky invaders and set goals once lose tracing. Besides that, our offensive staff will innocently come into a danger zone and be eaten by suddenly appearing ghosts. Secondly, our game strategy should be flexible and comprehensive to fight other teams which can be radical or conservative. Although there is the same goals that offense is the best defense, being aggressive means losing your own ground as well. Maybe it is easier for 2 cooperative defenders to catch the Pac-Man, but if you want to win a game, you must try hard to earn scores as much as possible. Last but not least, the layout is randomly generated in practical contexts. Therefore, our agents should be robust enough to cope with various situations haven't seen before. Every movement is a delicate evaluation to maximum the benefits and avoid pitfalls. Particularly when facing choices, it is not easy for Pac-Man to trade off between greedily carrying more foods and retreating home to earn points safely. Part 2, Techniques and Implementation. Our first implementation is an approximate Q-learning agent that learns weights from features of states based on a feature function. As a reinforcement learning technique, it updates the weight vectors and performs the action with the highest Q value at the probability of 1 minus epsilon. Otherwise, choose a random action for exploration. In order to get the score safely, we took a simple strategy that the Pac-Man will navigate to the nearest retreat point once the number of foods carried reaches a threshold to deposit, then start to invade again. Here, we extracted several features for the offensive agent, including its food, of course, its capsule, closest food, coming ghost, and ghost 1 step away. We trained this function for 200 episodes and get a learning curve like this. Yes, you must have observed that we encountered the problem of the long simulation trajectory, especially for the feature eating capsule. After all, it's hard to say if eating a capsule is conclusive to the result of a game. Instead of the far goal state, maybe we can try to terminate at some intermediate non-goal state and optimize features. However, we didn't dig deeper as we thought learning-based technique is time-consuming and quite challenging. The final submitted implementation of our team is based on techniques we talk about later in this video.
Our second implementation is based on A-star. A-star uses a cost estimate function which combines the current cost and the heuristic cost to the goal to determine how to extend the path all the way to the goal. At each position, our model needs to choose a goal position depending on the circumstance. A goal can be the position of a food, a capsule, or a retreat position. Because at each position, circumstance changes, the planned path given at the previous position could be outdated and needs to be updated. Therefore, our method is, at each position we calculate a path. We take the first step of this path to the next position, then we calculate a totally new path and take the first step of this new path. This process continues until the end of the game. Although planned paths might change at each position, we try to keep the goal persistent until it is achieved, to ensure persistent behaviors and high performance of agents. For example, if the Pac-Man sees any ghost coming and a capsule exists, the agent would set capsule as its goal as long as it is reachable, despite approaching defenders. For another example, when our Pac-Man is being chased by a ghost, it would set foods that are not in the corners as goals, although the ghost might just be one step away. Because of limitation in the agent's scope, sometimes Pac-Mans are invisible to ghosts, but we can still infer its location by comparing the food list of the previous game state and the current game state. If a food is missing in the current food list, then it must be eaten by a Pac-Man, and we can infer the Pac-Man's position or goal in the next few moves based on the missing food's position. This handles the scope limitation challenge properly. All Pac-Mans of the opposing side would have to set the border of our side as intermediate goals to invade into our side. Because the border is quite long, it is inevitable that we have blind spots on our border. We solve this problem by picking a standby area and keep patrolling. This method increases the difficulty for our enemies to invisibly invade into our side. Therefore, we integrated patrolling and prediction of invaders' next goal to build a more solid defense system.
Part 3. Dual Model Agent. Using A-star heuristic search achieves good defense in Technique 2. This is because we almost always have a clear goal at each step. However, in offense, it is hard to define the best goal when attacking or being chased by a ghost. Should the goal be our nearest food, a capsule far away, or return our own home side? Can we balance them or even reach them simultaneously? Thus, we design multiple heuristic scoring functions for each scenario to gain more benefit in the long term instead of defining a single goal. For example, while escaping from the ghost, we still can approach safe food in the open area, which is marked as green in this sample picture. Based on this idea, we pre-labeled open area and deep trenches before the game starts, which is marked as yellow. They are treated as a part of features to improve the scoring quality when chasing by ghosts. In this way, our Pac-Man can avoid pitfalls but still hunting food in the meantime. To resolve the trade-off between radical and conservative strategy, we define a return-reward factor as a feature. The heuristic insight is the more food Pac-Man is carrying, the closer to our border, the more benefit to return. We can see in the demo that Pac-Man finds it is better to return carrying food than keep hunting more food when our border is quite close. The most difficult part of offense scoring function feature selection is to achieve keeping hunting, seeking capsules, avoid pitfalls, and escaping from the ghost all at once. We use pre-labeled layout information and features from updating states dynamically. In this demo, Pac-Man finds it can race with the ghost to eat food, avoid entering deep trenches, and finally reaching the capsule. Sometimes two agents will attack cooperatively. For example, when our defense agent is scared. However, the challenge we faced is they can keep targeting at the same food and lower the efficiency. We improved this situation by using position information as feature to predict offense agents target food in following terms and go to another way.
Part 4 Discussion and Future Improvements. Although our rule-based approaches can outperform the Q-learning method for now, it is impossible to generalize to all circumstances. Every goal decision and scoring function has blind spots. Moreover, it is hard to find appropriate features and difficult to observe long-term reward for learning-based approach. However, if we have huge training data and resources, methods like deep reinforcement may reach a generalized model human cannot imagine, just like AlphaGo. First, in the short term, we can improve goal recognition more precisely. For example, instead of running after a Pac-Man, passively, we can actively predict the Pac-Man might enter in a trap and stand by at the position this Pac-Man cannot see. Second, to enhance our learning-based method, we have an ambition to frame it as a supervised learning problem and train step by step, use neural networks and all observable position information as features. The output direction of rule-based agent can first be viewed as human-labeled golden class. If the learner chooses the same direction as humans, it is rewarded. Using a rule-based agent to teach, learners can avoid the difficulty in defining long-term reward. After the learning model converges, we can furtherly use more training cases and even transfer learning technique to improve it. Third, another improvement proposal is to integrate other methods like multi-color tree search or game theory methods to vote for the next action, make our decision more informative.